All right, so questions?
So for the ODP,
Mm-hmm.
the output, you want it to be like, if you, use like a phrase or something, do it with like the letter twice, and then the first letter twice, and then the second letter twice.
You mean if you use the same phrase for both arguments?
Yeah.
Yeah, that would probably be the right thing to do. So your goal in this ODP is to write a function named mix. It takes 3 strings as arguments. Okay, the first 2 strings are null terminated strings that have some set of characters in them, and you can assume that they have exactly the same length, so they have the same number of characters as each other. And then your function should modify this third argument, which I called out. So that out is a null terminated string that's the interleave of the 2 input strings. So if you call this thing with, if you say mix, let's just do A, B, C, and 1, 2, 3, and out, where out is a character array, then out should end up being A1, B2, C3, and a null terminator. Okay, so mix takes your 2 input strings and just interleaves them together and stores that in the output string. So your output string, yes?
What is it? Okay, so you have the mix function as return int, right?
Yeah, and it doesn't matter what you return.
Okay.
I just made it int because I didn't want to get into voids. But there's nothing in here that says what the actual return value from the function should be, this int. You can just return 0 or 1 or whatever you like.
If you're writing like with the main function and you want to use this mix, it'll return an int for you instead?
Mm-hmm. But the
end.
int.
You want it, okay, so I thought you wanted to return the out.
It's modifying it.
It's modifying out, right? So normally when we say return from a function, we mean this thing, this int in this case, right? But there's other ways we can return information from a function, such as modifying an argument. Okay, and that's what you're doing in this case. This third argument out is simply there so that we can load something into it. And then your main program should use that third argument and print it out to test it or whatever you want to do. Yeah. That's a \0 at the end.
So what are we returning then?
Doesn't matter. I don't do anything with the return value. So I've talked to several people today already saying that they wrote their code and they're not getting 10 out of 10 on one of the tests, right? And everybody who's talked to me about this, my answer has been the same. When I look at their code, they're not null terminating the output string. So if you take in A and B, your output has got to be, this interleave of characters from A and B with a null terminator at the end, okay? If you set up your loop a certain way, that will happen for you. If you don't set it up a certain way, you're going to have to put that in yourselves. But one way or another, you got to make sure there's a null terminator at the end.
Wouldn't the output string be twice the length minus 1? Because you're removing one of the null terminators?
It depends what you mean by length, yes. So if you include null terminator in the length, you're exactly right. It's twice the length minus 1. If you don't include the null terminators, if you just look at the characters themselves, then it's twice the length. But declare your arrays and your test program to be big enough that you don't hit the edges. Right, so if you're testing with A, B, C, 1, 2, 3, make your arrays like 100 characters each. But yeah, you're right. If it's going to have one fewer elements in the whole array, because there's only one null terminator. So, problems you run into trying to get this to work? Other than not having a null terminator? So I'm going to suggest that if you run into issues with this, first course of action, post something on the discussion area of Canvas. Okay, let's get some groupthink going on this. There's a good chance I'm not going to be online much this afternoon, this evening. But if you post on the discussion area, I'll get an email about it, right? And I'll look in when I can. But there's a good chance somebody else will be able to help you with this. Now, if you have something particular that you need to talk to me about, always email me, right? If you're locked out of your account or something, right, send me an email. But if it's like, I don't know what I should be doing here, or you know, something like that, try the discussion area first. So let's talk about this business of returning information through this third argument. There's some nuances around this. So we spent a while, a couple of weeks ago, looking at this idea. If we have a main function that sets an integer n equal to 5, and then we pass that integer to a function, and then we print out the value of that integer, it's always going to be 5, right? There's nothing we can do in function that will change this n from being anything other than 5. And in our function, if we write our function, it takes an argument that I called arg, and we set that equal to 10. That does not change n to 10, right? And the buzzword is we're doing pass by value. So when we call function n, we're effectively saying function 5. And down here, all we know is arg is equal to 5. Nothing to do with n. But I'm making a liar out of myself, it seems, because I'm asking you to do this in your ODP. So here's what we have. Here's your main program. Here's your character array. Let's say it's 120. And we're going to call our function. We're going to pass it that string out, and then we're going to print that string out. And the claim is that somehow our function is going to be able to change what this string looks like. Call it s. So here's our function, takes a car pointer s. Yeah?
Is it because out is an address? So
Yeah, it's because out is an address. So inside here we might do something like s bracket 0 equals x, s1 equals null terminator, and return. And when we come back here and we print out, we're going to see a string containing the letter x. So let's debug this. So here's some test code to go along with this. We have a function that's going to take a car pointer. And then our main program makes an array of 100 characters, passes it to our function, then prints out the value of that string out. And our function takes a char star s, and I'm just filling it up with 8 x's. And then a null terminator, and I'm returning a 0, and just like RODP, I'm not doing anything with that return value, but it keeps us from having to say void. So that's our whole test code here. So let's go ahead and run this. Right, and so it apparently works fine. Right, our output string is equal to 8 x's, and we set that up in our function. But let me show you something. Suppose I don't do that. Suppose I don't set that null terminator to a 0. And I run this, my output string has stuff on the end, right? Because there happened to be stuff in memory. Now suppose I want to set my output string to be a set of 5 x's. So same thing, I'll set s0 through 4 equal to x, and I forget to put a null terminator on the end. Well, it looks like it works perfectly, right? Why? Because it just so happened that my first 8 locations in memory where I was storing my string were already filled with nulls. Null's probably the most popular byte to put in memory because I don't know why. There's lots of stuff that's null. So sometimes you get lucky and you look at this and it works fine, and sometimes you try a different test case and it doesn't work, right? So this makes debugging a bit trickier because you can write really good test code and still not necessarily catch the errors. And this was happening in people trying to assess their ODP last night or this morning. So you really got to go back to your code, and the big hint I'm giving you in this assignment is make sure you're putting on a null terminator, right? So if you're getting flaky behavior, that's the first thing to double check. So let's put this back in, and let's go ahead and do some debugging. Not to fix bugs, but to see what's going on. So I'm about to call my function, and I'm going to pass it this variable out. So I can print out, and out has stuff in it, and you can see it's got a bunch of nulls in the beginning, and then it's got some things that are not null. So where is out stored in memory? It's stored at 7FFF, bunch of stuff, E330. Now I'm going to step into this function call, and now I'm inside my function func, and I passed it an argument s, and if I print s, s is equal to exactly that same number. So 7FFF, blah, 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 E330. And we're about to say s bracket 0 equals x. Okay, s is an array. So the symbol s itself is a big long integer that's actually a location in memory. And it's actually the location in memory where the first element of that array is stored. Now when I say s bracket 0, how that gets coded into assembly language is it says take s, which is the address where the array begins, add 0 to get to the first element, and that's the memory address where we want to store x. So this basically writes an x into memory at this location. So let's make a memory map. And if I examine this location before I make this assignment, it's got a bunch of zeros in it. If I go ahead and I execute that instruction and I examine that memory location, that first byte, right, location 30 is on the right, is changed to a 78. That's a character X. So this has written an X into this location in memory. And when I execute the next instruction, now if I look at those locations in memory, that second location also has an X in it. Right? So that's location 31. That's got an X. And so on. And eventually we'll write a null terminator. And then we're going to return and now we're back in our main program. Well, remember, where's out stored? Out is stored at E330, right? This chunk of memory down here, which we were calling S in our function, is also what we call out in our main program. So they're really referring to the same locations in memory, right? We've got a variable in out, we called it function, and we passed that. This and this are exactly the same value. They have to be because we pass by value. When we called function out, we didn't pass a bunch of characters. We passed an integer, which was this big long memory address. And so inside our function, s was equal to the value that we passed, that big long integer. So both of these pieces of code are pointing to the same location in memory. This calls it out, this calls it s. When I update values in this array S, I'm updating these locations in memory starting at E330. When I come back to main and I look at my variable out as a string, I'm looking at these locations in memory. And they've been modified by our function. Okay, that's basically why we can pass strings back through function arguments without having to do an ampersand. It's because that ampersand is already there for us. When we say out, we're really saying address of out bracket 0. But that's possibly more confusing to think about. So yeah, if we try to examine out, it's going to be those locations in memory, and we just worked very hard to fill those up with 5 X's in a null terminator. So that's what's going on in your ODP, right? Now, you don't need to understand this level of it. Right, you're just going to have an array of characters, and you're just going to say, you know, out bracket 0 equals this, out bracket 1, or out bracket I, or whatever. Right, but that's what the passing mechanism is that's actually going on. All right, does that help at all? So let me make a few more comments on makefiles. The first comment is something I alluded to yesterday. We can put variables into our makefiles. And what I've done here is, instead of saying GCC, I've created a variable called ccomp, ccompiler, and I've set it equal to GCC. And anytime that I say $parentheses ccomp, this gets replaced by the value of that variable. So usually we compile C code with GCC, but on some systems the compiler might have a different name. On some systems we might want to use a C++ compiler, and this might be C plus sign plus sign. And instead of having to change all the lines in my file where I reference that compiler, I just set up a symbol for it. Okay, that's not terribly relevant for us, but this first line is. Sometimes we want to compile with the debug option, this -G, and sometimes we don't. So I put, after my GCC command, this expansion of the variable compile flags. And if compile flags is equal to G, this looks like GCC space dash G space the rest of this stuff. If I set compile flags to just be nothing, then this is going to look like GCC space dash O main, etc., etc. And there's no dash G switch. So I can turn on or off that debugging option just by changing this first line of my makefile. And it saves me from having to go through and edit all the lines where I say GCC. But mostly it stops me from having to understand anything about this makefile, right? Because there may be some things that I compile one way and some a different way and so on. So when you're making your makefile, right, which is a whole science in itself, you can leave yourself flexibility like this. So I can say make, and it just uses my regular GCC. And I run my code, and it's not working, and I want to go ahead and add debugging, so I'll add a dash G switch, and I'll say make. Well, it tells me main is up to date. All right, so you got a few options. You can do this, but I don't recommend it, right? Because if I accidentally type a space after that asterisk, I erase everything in my directory. It's happened. And there may be .o files that aren't part of this program that I don't want to erase and so on and so forth. But you can do that. And then when you say make, it's got to recompile everything. You can use touch, which just updates the modification date on all these files. Oh, but that doesn't work. Oh. Touch your .c files. And then it'll force it to make. But now I've changed the modification date on my .c files. And if I want to know later on what did I do, when was the last time I changed this, it looks like I changed it at 11:30 on Thursday, when in fact I might have changed it a week ago. So there's a better way to do this. So make doesn't really know anything about C programs. It doesn't know anything about modularization. It doesn't know anything about CSE 224. It's really just kind of a sort of very straightforward literal tool that reads this file, looks for targets, and follows recipes if dependencies are satisfied. And we can trick this into doing all kinds of things. Okay? So here's one thing that you often see in files. We'll see a bogus target called clean. Okay, and I'm not going to list any dependencies here. And if I say make space clean, it's going to say, is there a target named clean? It's going to come through and it says, oh yeah, here's a target named clean. There's no dependencies. Okay, I'm going to go ahead and execute the recipe. And my recipe for making clean is going to be to remove all of these .o files in the main program. Now, I'm not creating an executable program named clean. I'm not making anything. I'm actually getting rid of stuff. But make doesn't care. If I say make clean, it's going to say, okay, here's the recipe for clean. I'm just going to execute this command, and it'll remove all the stuff that I want to remove to do a clean rebuild. So I can say make, and it says main's up to date. If I say make clean, it gets rid of all of that. And now if I say make, it forces it to rebuild everything because I got rid of all the objects in the executable. And now if I try to make again, it'll say it's up to date. And so you'll find lots of things in make files. A lot of make files have something called install. So that when you say make install, it might copy your executable program into some system directory like /bin, right? And then when you want to build your system, all you do is say make install, and you're done, right? But it really doesn't care. Right, so here's a target called me laugh, and it just echoes haha. And if I say make, this is really stupid. If I say make me laugh, it echoes haha. Right? It can be anything. And usually when we build a make file, it's so that we can compile a bunch of code and link it all together. But you can do other stuff with this. So I do a lot of text processing in Unix, and there's a bunch of steps you have to perform, and sometimes I'll make a make file. So I can just say make, and it goes ahead, and it moves everything over, and it runs the text processing commands, and it builds a PDF of the output, and it copies it somewhere, and then it prints it for me, right? And I don't have to type in all these commands. So you can do pretty much anything you want in here. But make clean is a pretty standard option that'll let you get a fresh build, right? The other reason why you might want to do this is if you build your system and you bundle it all up into a tar file and you give it to somebody else and they're running on a different architecture, you've got an x86, they've got an ARM processor. If they try to run that executable program, it's not going to run. If they try to compile with your .O's, it's not going to compile because the ones and zeros are different. But if they say make, it's going to say everything's up to date. So they're going to have to go in and remove the .O so that it forces to recompile and so on. So if you have a clean option, they can just say make clean and then say make. So that's another reason for that. All right, so if there's no questions on that, I want to go to the board. I want you to go to the board. And I want you to work on algorithms. And so here's an algorithm to work on. So you're going to write a function named clean that takes an input string in and it's going to return an output string out. Okay, similar to ODP 413. And what it should do is remove all of the letter X's from in. And out should be a copy of in with all the X's removed, basically. So if in is X ox B, out should be HEOB. And these are null terminated strings, so keep them null terminated. And what I'm looking for is more pseudocode than C code. Okay, I want to see an algorithm for doing this. And if you write algorithms in C by your nature, that's okay, or Python or whatever. But I'm looking for the steps that you would go through, right? What's the recipe you would give someone on a desert island who was bored and thought they were a computer? What are the steps you would tell them to do to take an input string and turn it into an output string, which is an exact copy except there's no X's in it? Does that make sense? Okay, so I'm going to ask you to break into groups, go to the board, and write some code to do this.
I don't think we should get into like, we can just write out what we want it to do.
Like I just have it where it's pretty.
Word for word. Well, you're thinking about how you actually do it instead of thinking about how the algorithm should go. I think we need to think more about how the algorithm should go.
Oh, really?
So we can start with a start. And now we want to establish the inputs. So carry
And you can do flowchart or pseudocode. I'm okay with either.
Yeah, right.
If you want to,
how will we do it before we because we gotta loop through the link and
Well, we could just say check each character at the end.
right, that's what we're
I think we should.
Dude, I randomly like woke up this morning and didn't sleep. And I was like, no, I'm just gonna import this. And I found out,
Write
moved
the
like
character
2 a.m.
output.
Got everything like randomly. I couldn't get like Windows reboot on it.
I'd say like add character to the end of the word.
Well, you say end. We don't really know. Whatever. You know, I'm thinking about how I feel.
That's like kind of ready.
No, we're just gonna read right through.
That's pretty much it.
Right. Oh, yeah, right.
So like, as far as actually realizing that we probably need 2 counters, one to count the amount of characters that have been written out,
Yeah.
and one to count how many characters are in.
Yeah, I think that would be easier.
Well, it depends if we want to calculate how many X's were removed. If we just want to add it out, you don't need one count.
Because otherwise you'd be skipping spaces. Because think like if you have
Oh yeah,
could you be X?
So
Out is gonna be
yeah.
But if you have a separate counter, it needs to be X. And it's B.
I'm thinking more about. Yeah, and C. Yeah, we would do it like that. I was just thinking about when I've worked in other languages where the arrays will have like an add function, and then
Oh.
just do add, and then the character you want to add it, and it'll add it to the end, and you don't need to keep track of the spaces.
Yeah, so you just have an if statement, and if there is an X, you just,
If there is an X,
you don't
Don't
increase
do
the counter,
anything.
yeah.
So are you drilling down into this now, or is that your final?
Do we need to make a?
So that's a good high-level view. So write some more detailed pseudocode, assuming that in and out are arrays, to do these things you've described. Check each character for an X, add something to the end, and so on. So flesh that out.
Treat it like the box thing.
Nope, you're just giving a pointer to a character. So array, yeah, in and out.
Or would it go?
Well, no, you have to wait this because it's a
Toss me one of those.
like that.
Oh right. I probably would not equal that.
Doesn't matter. Did you just do
Like, this is just a catch, like we don't do anything.
Yeah.
Okay. So first, so I have to make 0.
It gets, this is just useful.
So do we want that back first in the while loop or?
It's at the end of the while. Like,
Oh, okay, you're returning the out. Yeah. What are you returning?
yeah, I just wrote the program. I finished it yesterday.
Whatever we're changing here is
You could change all this into a
Alright, so what
line.
about initializing I to?
That's literally.
Online, that sounds nasty.
Line equals to it, so.
That's okay. And your first diamond, that looks more like an if than a wow. I mean, it's the if at the top of a while loop.
But since you're not doing anything with this part, so you're not used to this part.
So we're like,
You could inspire me. I'm sorry.
Basically, you just change this into not equal to else.
Oh, yeah.
So then you just does this else, but you don't need an else, because it's still conjunction.
Okay.
So it starts off at 0, so i's, and then we have the null terminator.
that's what I would have done. I would have done.
And print in I to out I 2, you really mean out I 2.
I just like to do things with the least amount of line as possible.
Because that should actually be reversed. But you can change that equal to an arrow if you want.
Which means that if let's say that.
Brackets are terrible.
That would work.
Don't even try. It's the charm point.
But at the same time, it might skip. Basically, that's all.
Okay.
Yeah, that's like I said.
Everything is initial.
You don't initialize J to 0, you don't know
So
what it's
try
going to
another one which basically takes two strings.
Oh, geez, yeah. We need to.
Or is it gonna put a random?
be. It's just gonna, whatever was in memory, the part that I put it as gonna be there.
So let's say we're on this first one.
It's a little trickier than it seems at first. It's a little trickier than it might seem.
Not equal.
I can eventually.
I was thinking of 4.
I have mine here.
When I'm at home or something, it's like, okay, I don't play forward.
What you got?
So
Yeah.
it's just gonna increment.
I know, isn't it insane? It's like, it's like,
That's okay. So while I is less than string length,
yeah.
if j is not
I've done that
x,
too with like.
and I is not x, now j equals I and increment j, and go ahead and increment I.
I'm just like.
Alright, so that's copying over things that are not x into the output array. Everything's initialized to 0.
Yeah, yeah.
So last question, does this leave a null terminator on the output string or not? Yeah. Okay, so if you do it less than or equal, then the last character is a null terminator, it's not x, so it gets copied, so that works. And if you do it strictly less than, then you can just write a null terminator at the very end. Okay, cool, perfect. So you got several minutes left, so try another function which basically takes two input strings, tells you if they are the same.
Yeah, in one.
Let me grab an eraser.
You gotta do like the string.
2 input strings.
It's just better. And take the out, you can do the out.
Yeah. Yeah, so we just over to the,
Car array?
I just want to make sure all the elements of A are equal to the same as the elements in B. Some sort of loop.
We had two different strings.
Okay.
Is there another one out? Like,
You do a while.
so this is not, you're gonna have to
I
do
see.
another.
Okay.
Let's just change that.
We can just go while
Okay.
Yeah, I would do a while. I is less than the string length of A, less than the
While the same thing, keep looping until you're not.
Okay, so try this.
Right, so do it while
I do less than we include the null terminator.
Or
And then since we're checking that there's the same, well, we actually do, before this, we probably want to do an if statement and check that the string length of A is equal to the string length of B before we start the while.
Yeah, or because
Because it could technically, but it could technically be that the first 10 digits of A are the same as the first 10 digits of B, but A ends at 10 digits in, and then B continues on.
I think for this case, we don't need to consider it because these are restricted to like they're both the same. So like we could add like a check. Check if the string lengths are the same. If they aren't, then return. But that could just be at like the start of the program before the while loop.
Well, yeah, so then do it, like do it right here, do an if statement there. Okay. For the string lengths are the same. That's what I'm saying.
Yeah, yeah.
So this is like zero starting the channel, that's gonna be an A, okay. That's the end of the if, that's the end of the or if it's not, I gets incremented to 1.
If it's not equal.
Change your I to 1.
If it's equal, I saw like brackets.
If it's not equal, then return.
Oh yeah, yeah.
Okay, so
We probably want to return like a -1 too, since that's an error.
now we're gonna have a, instead of 0?
Yeah, because like 0 usually means your program ran without
I'm
fault.
not getting that in depth. You don't need return code.
Let's say,
What do we use for differential? Variable that
Yeah, so I is using I from there, so you're saying if AI is equal to BI.
char, like,
And well, you really, I would check, I just do.
Don't set them to each other.
Yeah, you check if they're equivalent.
let's say you return.
Actually, probably what I do is check if AI is not equal to BI, then return -1, but if it makes it to the loop without returning -1, I just return 0, and then you're done.
Oh, really? That's good.
It'd be just.
Couldn't you just set like an integer to the equivalent? Like set int I to the statement AI equals B.
Yes, you can return.
True.
This is equal to 1,
Then they return.
Okay.
Save program term.
Yeah.
I do that all the time.
So where does it give you your answer that's the same or different? Which branches are
I did a lot better than
Return, just like doing another return -1 or -2 or something. It's a different error value.
Do you know how it's called in our, this one? The one
And then.
Okay.
Wait,
You don't need anything else. You're just returning if they're not equal. If it gets to the whole while loop without triggering that return, then you know that it was success. So you just And then at the end of the while, after the while loop, just do return 0 and return 1.
I've never heard of again 1 for success.
Well, for scanf, it returns 1 successful.
If it writes 1 character, it returns 1.
Yeah, it writes 2 characters, it returns 2. But we've always used it with 1 character. One thing.
I'm just saying, it doesn't return 1 for success, it returns 1 for 1 character.
I think that thing that says no on your first diamond basically
Well,
says
you put the return
minus
out.
one says they're different. That works.
That can be A or B, so we'll check it if they're equal to each other.
All right, so we're just about out of time, but it looks like everybody is on the right path. Are you on the right path? Yes. Okay. So the key to making this work, right, is that you have 2 pointers. You have one pointer that's tracking the input string and another pointer that's tracking the output string. And because we don't always have the same output as the same input, right, those pointers have to be independent of each other. So you increment the input pointer and you move through, and if you want to copy it to the output, you use the output pointer to tell you where to write that character. If you hit an X, you just increment the input pointer, but you leave the output pointer where it is, right? And this motif pops up again and again anytime you're doing string processing or doing any manipulation of 2 structures. Usually you find yourself having to have 2 pointers, one for input, one for output. So it's a theme that'll come up again and again. And then of course the other thing is make sure there's a null terminator at the end, right? Because if you stop processing input as soon as you see the null terminator on the input, you haven't necessarily copied a null terminator to the output. But you've got an output pointer, right, J for most of you, saying where's the next spot I'm going to write to the output. So at the end of your loop, you can just throw a null terminator on output bracket J, and you're good to go. Okay, so that will make future ODPs. I think this is a future ODP, so you got to head up on it. Cool. Okay, so so tomorrow we will talk about Lab 3. We'll talk about questions from Lab 2 and any other questions you have, and then we'll move on. Okay.
So let's say you return 3, 4.